Good morning. Here we are at the video lecture, the physics video lecture, physics 2A video lecture 30. Okay, I'm going to start off with a couple of requests. So we had interest in seeing the quiz number 6 worked and problem 90 from chapter 8. Okay, so the first thing we'll do is quiz 6. Second thing is we'll do problem 890, and then we'll look into some other material. So for the quiz, we had on an incline, we had a mass, no friction situation. So we had equal masses here, M and M, and we had an angle A. I used angle A, and of course, down is in this direction here. And we wanted to get the acceleration of the system. So I'm just going to solve the entire problem here. And in fact, I think I'll write it down just as a good review with M1 and M2, and then we'll, specialize it for equal masses. M1 and M2. Okay. Because what we're looking at is the Newton's law for each one. We've got tension and tension. We have a normal force and a weight, but we're not going to need to know the normal force, or not going to need to use it because there's no friction. And we have, and so this was an M1G and this would be an M2G, right? So we write down Newton's law, net force equals MA, and we do it for M1, and we're going to have T minus M1G sine of A, since I'm using, well, that's what I had in the quiz. I'm going to go ahead and use alpha. Okay. Is equal to M1 times A. Okay. That's because we have the decomposition of this force, and this one here, this downhill one, that's the M1G sine alpha, pointing back. Okay. So good, that's for mass number 1. And for number 2, we have to remember that the positive direction is down, because here it's a continuation of the uphill motion there, so the positive direction is down. So we have M2G minus T, T's pulling up, is equal to M2 times A. So you have 2 equations and 2 unknowns, and you can solve for A and for T, or any 2 unknowns you want, but what we're going to do is add these 2 equations, because then we get M2G minus M1G sine alpha. That eliminates the tension, T minus T0, and then on the right side we have the sum of the 2 masses times A. So we can get the acceleration out of this formula right here. Okay, so acceleration, we'll just divide both sides by M1 plus M2. Now, at this point, I think I'll specialize it for equal masses. So M1 equals M2, because you'll see we get a nice simplification. We're going to get A is equal to m, so M1 equals M2 is just going to be M, so we have 2m, and then we have mg minus mg sine alpha. And you'll see the masses canceling, and G is a common factor. I'll put that right down here. Equals G times 1 minus sine of alpha divided by 2. So there's our answer. Okay, G's factored out, 1 minus sine alpha of 2. That is the answer. Equals this right here. Okay, so that was problem or quiz number 6. The other problem, 890, actually pretty interesting. So 890 was this cylinder that's been wrapped with a string. So it's just unwinding under its own weight. It's unwinding and falling down. So here we have to, how about we do a bigger picture? Just to make sure it's all visible. So here's our cylinder. Okay, it's just unwinding there. What are the forces on it? There is, let's do this one in blue. There's the tension. Okay. There's this tension. And then there's the weight mg. Those are the two forces. So there are two things going on here. We have Newton's law. And I'm going to put the positive direction down. Works well right here. So then we have the net force is T minus, or mg minus T, minus T plus mg is equal to ma. Okay. But of course there is also Newton's law for rotational motion, and I'll put that here. Tau net is equal to I alpha. And of course we have alpha R is equal to A. We're going to have to make use of that as well. So for this equation, the torque around this axis right in the middle is just T times R. Let's go ahead and label that we have the radius R here. So we have T times R. I is 1/2 mr squared. Moment of inertia of a disk, okay? And then alpha is, alpha is A divided by R right here. Divide both sides by R, so we have A divided by R. And now we're going to see, we can cancel all of the R's in this equation, and we get T is equal to MA divided by 2. Okay, R's cancel, MA divided by 2. So we can plug this expression into here. Okay, that'll eliminate the tension. So we'll have minus MA divided by 2 plus mg is equal to MA. And adding MA over 2 to both sides gives us 3/2 m times A, right? 1/2, 3/2 m times A, and this gives us the result we were told we would get. Cross multiply again, we're going to get 2/3 G. So as it unwinds, it accelerates with a constant acceleration, but 2/3 of G. It's not free fall, it's 2/3 of G. So yeah, that's the answer to that problem. The other parts of the problem are interesting as well. One thing about the linear speed of this thing, I'll use this part of the board. I'm just going to remind you of this old formula, V squared equals 2gh. We have that for free fall, so this is parenthetically, okay? But, so, we've got a 2 here. Now, instead of the free fall acceleration, we have 2/3 of the free fall acceleration. So, then I can just say 2/3 g and h, and that's where the 4/3 gh square root comes from that you have on part B. Good. The third way to do this was with energy for part C. I don't even know if I assigned all 3 parts, but this is part B here. This was part A. And part C was the energy method. So let's go ahead and send this up here. And the energy method, I may just set this up for you guys. Okay, energy, E sub A equals E sub B. That's the way we always do it. And we're going to drop through a height h. I won't even draw it up there. So it's gone through a vertical distance h, the center of mass has. So we would have just had at rest mgh to begin with for the energy. So all of that potential energy is going to be turned into kinetic energy when we drop through a distance h, and that's a half mv squared plus 1/2 I omega squared. So we have a half mv squared plus 1/2, and then now the moment of inertia of the disk, 1/2 m r squared, and then again the omega r equals v relation. So the omega squared is going to be v divided by r squared. I divide both sides here by r, so v squared divided by r squared, that's going to cancel these. We'll have 1/2 m v squared plus 1/2 times 1/2 m v squared. Etc. Okay. Good, so that's how that goes. And those were those requests. Now today's discussion, I have one more problem out of the rotational motion and circular motion field that I want to do before we move on into the next chapter. And I had almost forgotten it, but then I was asked to do a guest lecture on this for a colleague. And it's the hammer throw. So we're going to talk about some track and field events. We already mentioned the pole vault, and the hammer throw is also an interesting event. And I brought a big sledgehammer like this, but this isn't actually what the hammer throw is, but it goes back to this. If you were to go back to Scotland or something, they're hurling some big hammers around. So I'll describe what the hammer throw is in modern times. And it's an Olympic event, track and field event, and it uses just the right amount of physics. So I'll turn that into a homework assignment as well. So good. So the third thing right here is the hammer throw. So yeah, a sledgehammer would be what I'm holding right here, okay? And you could grab it by the end of the handle and whirl it as fast as you can and throw it. Hope nothing bad happens. The modern hammer throw, I've got a little mock-up here. It's a mass, a round mass. This isn't round, but it's what I have. On the end of a steel cable. I also don't have a steel cable, I have a cord here. So it's a mass at the end of a steel cable with a handle on the end, and the athletes whirl this thing around as fast as they can. They take a few turns and they release it, and they fling it really far. Okay, the world record, which I'm going to have you guys look up, is close to the length of a football field. And I'll have you guys look up the actual masses and everything else, and include that in your homework then. Okay, but yeah, so they're whirling something around. Imagine that tennis ball on a string that I showed you at one point, if I did. Okay, so let's get started with the hammer throw. So first of all, the hammer, it's got a handle here, so there's the handle. And there's a steel cable. And there is a spherical steel or some metal mass here. Mass M equals, and in fact what you want to find is it's a men's and women's event, and the women's mass M sub men, M sub women. Okay. Cable is almost the same length for men's and women's, but you may as well look that up as well. So cable L equals L sub men. It's only off by a couple centimeters, very close to the same length. L sub women. Okay, so there's a cable, and like I said, somebody's got at the end of the the handle is a steel cable, at the end there's the mass, and they're swinging around. Circular motion, release it, and it goes flying off across the field. So yeah, your homework is going to be to look this up, get some clips of this. I'll detail that later. But so far it's got a handle, it's got a cable, and there's a circular motion after which it's released and it goes flying. So cable length, good, mass M, two different masses. So then, one more thing. So hammer throw, and then we have circular motion. Which we've studied, and you release the thing and it goes flying. Okay, so now I'm going to draw what we need to know from these two fields. Namely, on the one hand, if you launch this thing, it's made of steel or iron or something, it's going to be true projectile motion. And before you release it, you have circular motion. So we're going to combine those two subjects. And the question we're going to answer is, what is the tension? What is the tension in the cable as this thing's being whirled around? What's the tension in the cable at the moment of release? Okay. And the answer is going to surprise you guys when you calculate it. So question, this is what we're going to answer. with our physics knowledge, what is the tension? How much tension, how much tension in the cable when the hammer is released, okay? So how much tension in the cable? And there are two parts to the problem. The first part is the projectile motion, which this thing most certainly is. Now, we've studied projectile motion. We know that if we launch at an angle theta with initial speed v0, it will go across here and end up at some range, okay? And we even know the range formula, R is equal to v0 squared sine of 2 theta over g. But we're trying to set a world record here, and so what we would use is the angle that gives us the maximum range, which is 45 degrees. And then the sine is just equal to 1. So we have R max is equal to v0 squared divided by g. So there's one of our ingredients. The second ingredient is circular motion. And there we've got Newton's law. F is ma, except it's mass times centripetal. So F, and this is the tension in the cable, right? We're whirling around in a circle. F is equal to m v squared divided by r. This is the radius of motion of our hammer. That's going in a circle. And look at this. v0 squared, these are the same two speeds. Okay? This is the speed this thing had as it was launched, and here it's the speed as it's being released from your hand. Okay? So these are the same speeds, and for that reason, we can just cross multiply v0 squared as g times r max. So what we have is the mass of the hammer, g r max divided by r. So this is what you guys are trying to calculate. Okay. This is the quantity you're trying to calculate. So you have to look up the masses, you know, for men and women. You can do both of these. G is going to be 9.8. These are the world records, the respective world record distances from the hammer throw for men and for women. Okay. And the question mark here is R. Okay, what is the actual radius of that circular motion? And the thing is, we've got the length of the cable. Okay, so you're going to look that up and you'll find the length of the cable. It's a little bit over 1 meter. Okay, so if this meter stake had, you know, a steel ball at the end and I'm swinging it around, the question is, what's the radius? And it's not that simple, because the athletes, as they're whirling around, they're not just a fixed axis. It's a little more complicated. And I'm not going to say I am going to say your guess or your judgment on that is probably as good as mine if you think about it. So we've got that somewhat more than 1 meter, and we have some length of the arms here, okay? But then the bodies can also be curved a little, so forth. So you're going to put in some number, and I'm just going to put a note here. R is some approximation to close to 2 meters or so. But this you want to justify. Have a look at the whole situation and see what you think. Probably less than 2 meters. So this is kind of a question mark. I'm going to say 1.8 meters less than R less than 2 meters, question mark. Okay. So you can see if you put in this range of values, you're going to get slightly different answers. You got to play around with that a bit. You can go right in between these two or something like that. That's complicated. You know, actually nailing down what that length really is. Okay, so I said I was going to turn this into a homework problem, so I will I'll do that. You're trying to calculate this number, maybe for the men and for the women. And finally, what you want to do once you have this is compare it to your own weight in newtons. Okay. So good. I'm going to send this up and then formulate the whole, the entire homework problem. Okay, so this is our hammer throw homework. And the first thing is to look up some good video clips of this. And take a couple screen captures and print them out and you know, send them to me along with your homework and or your notes. You can do them both in the homework and the notes. So view some videos of the hammer throw and print out some screen captures, some screenshots. Print out a couple of those to show me that you watched some of the videos on the hammer throw. Second thing is you want to find men's and women's world record. It's interesting, the men's world record was set in the 1980s. But yeah, you'll find that. World record distances. Those are our R max, right? Find them there. You can pretty much assume that they're going at a 45-degree angle because it's a projectile and makes a difference. So you want to find these. That's the R max. And then you need the parameters here. Find the respective masses of the hammer for men and women, different masses, and for the lengths of the hammer as I drew in my picture L. And when you have all of that, 5 calculate FC, that's that thing up here. For men and women. And note, you're going to have to state what your estimate is that you're using for this R here. After you view them, maybe you can come up with a better idea than I have. I say it's about between 1.8 and 2 meters. Yeah. So this is your calculation. And then finally compare this to your own weight. Now, if you don't know your weight in newtons, remember that 2.2 pounds equals 9.8 newtons. That's a conversion, so you can always convert to newtons. And when I say do this comparison, you know, it's FC divided by your weight. And that's going to be an impressive number. I'll tell you, it's more than your weight, and it's more than twice your weight, okay, when that steel ball is released. So this is a nice example of some of our physics put to work in the athletic regime. We had a sports physics 10 class, sports physics, where a year or two years ago now, we went out to the track and had some demonstrations by some of our own Fresno State athletes. And it's a pretty technical event. On the other hand, the physics of it, projectile motion, maximum range, and circular motion, is pretty basic for us now that we've done this stuff. So that's our assignment. I had almost forgotten this event, but I think it's a good one to study. So enjoy looking through this a bit. You know, you learn a lot just observing it, and you learn more when you put this physics that we know to work. Okay, I think I'm going to leave it at that. This is homework number 30. Let's see how we're doing here. Yes, that'll leave you some time to go look these things up. After this, we're going on into chapter 9 on fluids, fluid mechanics. So we still have a lot to do, but good. See you guys next time.